which starts out as empty because of the default constructor. And then we're invoking the insert member function 6 times on BT1. And we know that works fine, and that will build a binary tree object containing 6 int values in ascending order. But now let's suppose that the application developer wants another tree to maintain a copy of what the original BT1 looks like. Alright, so here we can say BT2 is a binary tree that's const. It's initialized with BT1. This works fine because the copy constructor for the binary tree class has been declared to receive a reference to a binary tree const. We cannot, as we would expect not to be able to do, say bt2.insert -5. That would be a modification to the binary tree object bt2, and so we don't want that to work. But our problem is that member function calls like bt2.size also fail. We get a compile time error from that, because although we know that the size member function does not modify the binary tree object that it's operating on, the compiler has no way of knowing that, so we have to solve this problem. What we need to do is to modify the definition of our binary tree class to indicate which member functions are allowed to be invoked on objects that are declared const. And the syntax for doing this is a little bit peculiar. What we have to do is to append the word const at the end of the member function declaration in the class definition. So that's shown here on slide 22. Here's our class definition, which is in a header file, almost certainly. Now, it's not possible for any constructor or destructor to be const. Obviously, a constructor that is building a binary tree or a destructor that's destroying a binary tree, these things are necessarily modifying the binary tree, and so they cannot be declared const. In the particular case of binary tree, insert is definitely modifying the binary tree, so it is not declared as a const function. But functions such as size, min, sum, mean do not in any way modify the current binary tree object. They're simply returning the number of elements in the binary tree, or figuring out what the minimum value or the sum or the mean of the values in the binary tree are. And so to indicate to the compiler that these functions can safely be called on a const binary tree object, we stick the word const at the end of the declaration. This is frankly peculiar, and it violates our inside-out, right-then-left data type reading rule. But the fact is that putting const at the end of the declaration is the only place left where const could be placed. If you had const at the beginning of the declaration, that would mean that the function is returning some kind of const. On the other hand, if you had const in the parentheses for the declaration of the member function, that would mean that one of the arguments was a const. So we can't put const at the beginning, we can't put const in the parameter list, so all that's left is to stick const at the end. Now here we have the assignment operator. The assignment operator will, of course, modify the current binary tree object to contain a copy of the argument binary tree object. So the assignment operator cannot be declared as const. However, the equality test operator, which is comparing the current binary tree object to another binary tree object, that is const because it does not change the current binary tree object. And here is good old put to ostream that we started this whole discussion with. Since put to ostream does not change the current binary tree object, it also should be declared const. So this is an added step in your definition of a class. Not only do you have to decide what services the class provides and implement member functions to provide those services, but you also have to go through each time you add a member function and decide whether that member function is modifying the current object or not. Member functions for any class fall into 4 categories. There are constructors and destructors. Then there are access functions and modify functions. Now the access functions only access information in the object, and so those are the ones that should be declared const. The modifier functions, of course, modify the current object, and so they are not declared const. Okay? So constructors, destructors, accessors, modifiers, and within those four categories, it's the accessor functions that should be defined as const member functions. So on slide 22, we've shown what you need to do in the class definition to declare that certain member functions, namely the accessor functions, are const. In terms then of those member function definitions, here on slide 23 we have an example for the mean function. All we have to do in the definition is to add the word const at the end of the declaration part of the function definition. So this says that mean is a member of the binary tree class. It's a function that takes no argument, it returns a double, and oh by the way, it's a const member function. Now if you define a member function as const, and then within the definition of the function in curly braces, you do modify one of the data members of the object, the compiler will yell at you and tell you that you can't modify the data of the current object within a const member function. So the compiler is smart enough to complain when you accidentally modify some data in a const member function. Unfortunately, the compiler is not smart enough to figure out when you are not modifying the data in the current object, so that the compiler could figure out for you which one of these member functions are const on the fly. So this is annoying and does put on you the responsibility of specifying the word const at the end of the declaration part in any function definition for a const member function. Since we have now declared put2ostream as a const member function, and presumably we've also modified the definition of put2ostream to have the const keyword at the end of the declaration part, we can modify the definition of our overloaded insert operator to receive the second argument, that is the right-hand argument, to the insert operator as a reference to a binary tree const. This says that BT is a reference to a const, and because put2ostream is a const member function, when we invoke put2ostream on the object BT, this will compile and run successfully. Now, we built our binary tree class on top of a whole bunch of previously developed lower-level binary tree helper functions written in terms of pointers to these BT node structures. So if we decide that we're going to update our binary tree class to specify that all the accessor functions are const, this is going to mean percolating this constness down through all of those helper functions as well. Here we're saying that size is a const member function of the binary tree class, so that means the helper function, binary tree size, had better be receiving the data member top as a pointer to a BT node const. Getting this hierarchy of constness correct in code that you already have written is pretty awful. Doing this retroactively is a pain. So now that you know about const member functions, it's much better to consider as you develop your class which of the function parameters and which of the member functions in your class should be const, so that you incorporate this constness from the ground up as you're developing your class. If we do make all of our accessor functions for our binary tree class const, and we do percolate that constness down through the various helper functions that those accessor functions use, then our application using a binary tree const object will work very nicely. Here on slide 27, once again we've declared BT2 as a binary tree const. It's initialized using the copy constructor from BT1. If we did attempt to insert a value into BT2, that would be an error from the compiler because insert is not specified as a const member function. On the other hand, size and mean are specified as const member functions, so calling size and mean on BT2 works fine.